Okay, here we are, lecture 27. So we just did a lecture on how if you've got a norm that gives you a metric, and if you've got an inner product, that gives you a norm. Okay, so you remember the way we get a metric from a norm is we just apply the norm to the difference between the two points. And to go from an inner product to a norm, we just take the inner product of a point with itself, and then we take the square root. Okay, and if we do this in Rn, our inner product is just a dot product. That induces the 2 norm, which is our standard Euclidean measure of distance. And the 2 norm induces the D2 metric, which again is our standard Euclidean notion of distance, okay? Frequently though, you want to work in a different norm. Maybe because your problem says you have to work in a different norm. Or sometimes it's nicer to work in the other norm. One thing that comes up quite a bit, and is going to come up in today's proofs even, is that it's frequently nicer to work in the 1 norm than the 2 norm, okay? The reason is that the things of norm 1 in the 2 norm are a sphere. But the things of norm 1 in the 1 norm are just a cube. Well, I mean, I'm talking about 3 dimensions, but anyway, it's a hypercube in n dimensions. And it's just easier to work with a hypercube than it is to work with a sphere. Okay, so our big result today allows us to just say it doesn't matter. I mean, for most purposes, it doesn't matter. We can use whichever norm we want. Okay? This is, in some sense, a repeat of some stuff in Tao's book from the first chapter. But again, I wasn't very happy with how we covered it there. And so now we're going to spend an entire lecture on it. Okay? Okay, are there any questions? If there are, just jump in. What we want to do first is define what it means for norms to be equivalent. So you get 2 norms. Norms look like this. That's your generic norm. It's just this double bars. The dot inside, again, means you put your point there. Now, if you want a second norm, we're going to do double bars with a star or an asterisk down in the subscripts. Okay. And then we're going to be talking, at least for this definition, we're going to be using an arbitrary vector space, but in our proofs, we're only going to be talking about Rn. Now, equivalent norms don't have to be the same, but they have to be the same up to a constant. There you go. So the star norm is sandwiched between a constant times the non-star norm and another constant times the non-star norm. Okay? Let's look at an example. I think this will clear up any questions you might have. let's look in Rn. I claim the 1 norm and the 2 norm are equivalent, and that we've already got all the material to prove that. Okay. So I'm going to do one direction here. Let's look at the 2 norm, but as is common, instead of looking at the 2 norm, we want to look at it squared. Okay. Well, that's just the sum of the coordinates all squared. Okay. The sum of squares is less than or equal to the square of the sums, well, the square of the sum of the absolute values. So we have that inequality. And that is the same thing as the 1 norm squared. Okay. So if we put the 1 norm in here, then we'd have the 2 norm over there with a little c equal to 1. Okay, what are we going to do for the other side? Let's look at the 1 norm. Again, that's the sum of the absolute values of the coordinates. Okay. Now, how do we get an upper bound on this in terms of the 2 norm? Has anyone seen it and would like to volunteer? I'll give you a hint. Here's your hint. No? Okay, remember from last time we did Cauchy-Schwarz. Cauchy-Schwarz says, I'll do it right up here if I can fit it in there. The inner product of x with y squared is less than or equal to the inner product of x with x times the inner product of y with y. And actually, let's get rid of that square. So I will square root both sides. We can do that because on the right-hand side, those are both positive by rules of inner products. Okay, and now I'm going to view this as an inner product in Rn of the all one vector, and not quite x, but it's the vector of the vector whose components are the absolute value of the corresponding components of x. Okay, so this would be equal to, sure, this is equal to the inner product of the all one vector with that absolute value of x kind of vector. Okay, Cauchy-Schwarz now says that that is less than or equal to the square root of this inner product of x with itself and y with itself, or in this case, it's the inner product of the all one vector with itself and the inner product of this absolute value x vector with itself. Okay? Now, if you work that out, the inner product of the all one vector with itself is just n, and we're taking a square root, so we get square root n. And then the inner product of this absolute value x vector with itself is the 2 norm of x all squared. So when we take the square root, we get the 2 norm of x. Okay, so that inequality was Cauchy-Schwarz, and we see that we get this inequality. So the 1 norm and the 2 norm on Rn are equivalent norms because square root n is constant for our purposes. Okay. We're not thinking about the dimension as changing. So that square root n really is a constant. Okay, any questions on that?
So we've made this definition of equivalence. I'm just wondering where the motivation for calling these two things equivalent comes from.
Oh, okay, yeah. So the thing about equivalent norms, and we've talked about this before, but I guess we're not going to have a result that really states this here, but I hope it's kind of clear. Like, okay, so take these norms and then look at the corresponding metrics. If you converge in one of the metrics, in one of the metric spaces, you're going to converge in the other metric space. Okay? And the reason is that the distance between points in one metric space is bounded by a constant times the distance between points in the other metric space. Okay, or another way to put it is just like closeness. In the induced metric spaces, the notion of closeness is the same, kind of. The actual number that you associate to distances changes, but whether two things are close doesn't really change. Okay.
So it's just the same reason for limits and convergence. We just have a constant. We can just set our epsilon to cancel it out.
Exactly. Okay. Yeah. So in terms of most things we would do in analysis, if you've got equivalent norms, it doesn't matter which one you use. Okay, you want to prove convergence, you want to compute a limit, all of this stuff, it doesn't matter. Okay? The other place where it doesn't matter is continuity. Okay, so a function is going to be continuous with respect to, well, the metric induced by one norm, if and only if it's continuous with respect to the metric induced by any other equivalent norm. Okay, so I mean, it's trying to capture the notion that basically the topology of the spaces is the same. Okay. Oh, so one definition before we go on to our main theorem. this is gonna come up in our proof, so I thought it was, and since it's important other places, I thought, we'd define it outside the proof. Okay, so your unit sphere is all the points at Euclidean distance 1 from the origin. Okay. Why do we put the superscript n minus 1 on it?
Because it's a surface embedded in Rn, so it's got one dimension less. I guess if you are on top of it, if you live on the sphere, I guess.
Exactly, yeah. If you live on the sphere, then that's a two-dimensional space to you. Okay? Or, the fancy word is that this n-dimensional, the unit sphere in Rn is an n minus 1 dimensional manifold. Okay? Now, we're not going to get into that. I just want to, note the notation that we're using. Okay. Now, Sn minus 1 is closed and bounded in the metric space Rn with the Euclidean distance. Okay. To see that it's closed, if you really want to check that it's closed, look at the complement. I think it's pretty clear that the complement is open. To see that it's bounded, well, its definition says it's bounded, basically, right? And so now I'm going to appeal, unfortunately, to the Heine-Borel theorem in Rn, which I believe we basically skipped. I think I said you should know that this theorem holds in Rn instead of just in R. So anyway, we're gonna use it here. Sorry that I don't think we actually proved this part. Although it's not that hard to prove this part from what we already proved. So, by the Heine-Borel theorem, what is the conclusion? Does anyone remember what the Heine-Borel theorem says?
Roger posted something in the chat.
Oh, I'm sorry. I need to remember to look at the chat this week, apparently. Yes. Yeah, if we have a closed and bounded set in Rn, then it is compact. That's the Heine-Borel theorem for Rn. Okay. Now, the way this is going to show up in our proof is we're going to use the extreme value theorem. So a function on the unit sphere, a continuous function on the unit sphere, will attain its minimum and its maximum. Okay. So now, for our main results. All norms on Rn are equivalent. It's important to note what this does not say. This doesn't say that all metrics are equivalent. Okay? Because there are metrics that do not come from norms. For example, you can check the discrete metric does not come from a norm. Okay. So we'll show in our proof that every norm on Rn is equivalent to the 2 norm. Let me get the light. Okay. If you believe that this is the notion of equivalence is really an equivalence relation, then this is all you need to do. And the fact that equivalence is an equivalence relation is not, it's not hard to prove at all. You just take your constants, write them down, multiply them, and you're fine. Okay? So let's let just this generic norm be any norm on Rn. Okay. Oops. I'm going to look the maximum of this mystery norm on the standard basis vectors. So here, EK is the kth standard basis vector of Rn. Okay, now in this class, every time we take a max, we should be suspicious, but we're okay. I mean, all of these things really do have norms, and there's only finitely many, so we can take a max. Okay? Now, let's let x be arbitrary. For any x in Rn, let's express it in terms of the standard basis vectors. Okay. Okay, so any vector is just the sum of its components times the standard basis vectors, and then we go to compute its norm. Okay, well, I'll just fill in. There we are. That's what x is. We already said that. Now, this is the sum of a bunch of scalars times vectors. By the properties of norms, we've got that linearity. So we can break this all up. Let's see. By the triangle inequality, let's take this one step at a time. By the triangle inequality, we have this. Okay. Now, norms say scalars get to come out if you bring the absolute value with them. Okay, we good so far? Any questions yet? Okay. The maximum that one of these norms of a basis factor could be is capital M, because that's how we defined capital M. And now what is this quantity that we've got?
That's n times the, yeah, Robbie had it in chat, n times the
Oh.
1 norm.
Yep. M times the 1 norm. And I said we wanted to show everything's equivalent actually to the 2 norms, so now what do we do?
Well, we know the 1 norm is equivalent to the 2 norm, so we could just use our work from above.
Yep, we use the inequality from above. We only want one direction here. So we get capital M times square root n times the 2 norm. Okay. So our mystery norm is bounded above by the 2 norm, by a constant times the 2 norm. What about the other direction? Okay. The other direction is a little bit tricky. It's certainly trickier. Okay, because for the other direction we want to get a lower bound on this norm. Okay. Let's use what we've got here. So it follows just from this direction. So we're going to look at the induced metric, the metric induced by the mystery norm here. Okay, and that's just so this part isn't a mystery. I mean, that's just that definition of a metric. We already know that since we're assuming that the bars are a norm, we know that that is a metric. Okay. Now, what can we say about this? Well, the distance between x and y in that metric is less than or equal to m times the square root of n times the distance between x and y in the 2 norm. Guess I should say. Okay. Now, what does that mean? This implies that the function if we define the function f of x to be the norm of x, the mystery norm of x, this function is continuous with respect to the Euclidean distance function, well, let me just say it this way. It is continuous in the metric space R to the n d2.
Can you explain that? I don't quite see that.
Sure.
And also this f function is going from all of Rn to R positive, right?
Yeah, sorry. So I can't really say this. You're right. I mean, so just notationally, I can't say what I just said. This is continuous as a function from Rn d2 to our normal, to the real numbers with the normal distance. Does that make more sense for that part?
Yeah, except this d is the standard metric, not the mystery metric.
Oh. Let me write that as d1.
Okay.
There we go. Yeah, that's unfortunate. Okay, now why is it continuous? Well, you can one way is just to write out a proof. Right, suppose we want f of x minus f of y less than epsilon. Right? Then take, this is showing us what we need to do. We need to take the d2 distance between x and y to be less than epsilon over m square root of n. Okay, so in fact, that's not just continuity that we just showed, that's uniform continuity. Because we don't get a different delta depending on which point x we're looking at. Does that make sense?
Yeah, that makes sense. And this sort of the reason we got this is because we've already sort of shown half the equivalence, and this is kind of what our equivalence likes to do. Where
Yeah.
we just have this constant, so we can, all the nice things come from it.
Yeah, okay, so we said earlier on, if you have equivalent norms, then you have the same continuous functions no matter the norm. Right, what actually happens is that equivalence of norms is two inequalities, and each of those inequalities says that if you're continuous in one of the norms, then you have to be continuous in the other norm. And we proved the one that we need for this implication. Okay, that if you're continuous with respect to the mystery norm, then you're continuous with respect to the two norm. Okay, we actually can't conclude the other one if you, I mean, we don't need it, but we can't conclude that if you're continuous with respect to the 2 norm, then you're continuous with respect to the mystery norm. At least I don't think we can. Okay. Now, we've got to continue, this norm is itself a continuous function in the metric space we need here. It follows that if we restrict our function to the n sphere, I guess the n-1 sphere, that this is a continuous function on a compact set. Okay. Let me just be clear, I'm talking about the Euclidean space right here. So it achieves its minimum. This is the extreme value theorem. Okay. Give that minimum the name little c. Now, we can say furthermore that that little c is not 0. Okay. Why is that little c not 0? Why is the minimum of the mystery norm on the sphere not 0?
So for it to be 0, we would need the vector that gave it, that spits this value out to be 0, which isn't going to happen because all of the norms and all of the 2 norms are equal to 1, so the vector isn't 0.
Mm-hmm. Right. So let me restate that. One of the axioms of being a norm is that you can only be 0 on the 0 vector. And the 0 vector is not on the sphere. Okay? Okay, so norms can only be 0 on the 0 vector, at the 0 vector, and the 0 vector is not in this set where we're evaluating f. Okay. So now for any x in our sphere, what did we just say? F of x, which is equal to the mystery norm, is greater than or equal to c. Okay? Now, that is sort of what we want. In fact, we can go one step farther. It's greater than or equal to c, which is also c times its 2 norm, because it's on the sphere, so its 2 norm is 1. Okay? That's the direction we want which is that. That's the direction we want. We want a lower bound on the mystery norm in terms of the 2 norm. Okay, so now there's kind of a standard technique to sort of propagate this lower bound to the whole space. And that standard technique is just unitization. Okay, you did this a bunch in Calc 3. We're just going to do it one more time. Okay, so now take any y, but we don't want it to be 0. Okay. So if we define x to be y divided by its 2 norm, that's on the unit sphere. And now we're just going to use some properties of norms, okay? The mystery norm of y is, I'm going to multiply and divide by the 2 norm of y inside there. So it looks really awful. There you go. Scalars can come out, so we might as well bring that 2 norm of y out. We'll leave, well, I mean, never mind. We'll leave the x in there. The mystery norm of x is at least c. That's it. We've got a constant c that gives us the other bound. Okay, so for every y in Rn, we have c times the 2 norm of y is less than or equal to its mystery norm is less than or equal to, what was our bound for the other side? M times the square root of n. Okay. I said every here, and up here I said not equal to 0. You should just check that, yes, if you plug in the 0 vector, this is still true.
We said that c is greater than 0, though, right?
Sure, c is greater than or equal to, c is greater than 0, yes. But this is still true for the 0 vector, because if y is the 0 vector, then you'll get a 0 there, and a 0 there, and a 0 there. Okay, are there any questions on that proof? Well, in that case, I'd meant to go into some applications of this to linear transformations. They're pretty straightforward, but we're not going to have time to state them in the rest of class today. So in that case, if there are any questions, ask them now. Otherwise, I think that's the lecture. Okay. Have a good rest of the day then. Maybe I'll see you at office hours today, or office hours tomorrow, or I will see you on Wednesday.